So hi everyone. So welcome to the course Mastering in Computer Graphics. So from pixel to worlds. In previous session, we discussed the classification of visible surface reduction algorithms in object space and image space method. And in this module 2, we'll be discussing about various visible surface reduction algorithms. So there are some 12 plus visible surface reduction algorithms are available in this module. And in this session, we will be discussing first three algorithms, that is back-based reduction, depth buffer method, and the A buffer method. So by end of this lesson, you will understand how these algorithms are improving in rendering the objects in a computer system. Okay, so let's start with the back-based reduction or culling. So here in back-based reduction is one of the most simplest and fastest visibility algorithm. It belongs to the category of object space method. So it is treating the entire object as one entity. So the basic idea is straightforward. When viewing solid object from outside, some polygon face towards the viewer while the others face away. So this is the viewing angle from the camera. So the hidden in this space, the objects is not visible actually. Okay. So the process of removing the invisible polygon is called as back face culling. So this dashed surface is actually back face culling. For example, the viewing cube is only three faces. That is what the hidden is actually not visible. And so to do this, we will understand few things. First one is whether the polygon faces the viewer or not. So based on this, we will be deciding. So first one will take surface normal vector n. So n is capital N is the surface normal vector, a normal vector perpendicular to the polygon surface. That is what capital N. Every polygon has two possible normals pointing to the opposite directions. So next one is L. Capital L is actually um, the vector points from the surface. The vector points from the surface is actually L towards the camera viewing point. Let the theta represents the angle between the viewing vector and the normal vector. A surface is visible when the 0 degree less than or equal to theta or less than or equal to 90. That is, so the theta should be lies in between 0 to 90 degree or 0 to 1, where the cos theta lies between 0 to 1. The cosine value is actually computed using the dot product of L dot n, where it is modulus of L and into modulus of n into cos theta. Okay, so if a dot product indicates the surface is facing away, the polygon will be removed. The normal vector itself obtained using the cross product of A and B, n equal to A and B. So the mathematical test allows the graphic system quickly identify the invisible polygons. And coming to this slide, so another way to determine the visibility through the plane equation. So consider the same polygon, hidden space is the gray area is a hidden space. So we are representing the entire thing into 3D space. So that is another way. So let us see how it is working. So coming to the a point lies behind the polygon contain again the capital A, so capital N, which will be represented in the equation ax plus by into cz plus d, which is less than 0. So here ABCD are the plane coefficients or parameters. So in many graphic system, the viewing direction is aligned with the z-axis. So in the z-axis, okay, the viewing direction. And we are having some cases. The first case one is if the C is less than 0. So the polygon is back face and it is invisible and it can be discarded. Okay, if the C is less than 0. Second case is if C is equal to 0, the viewing direction is parallel to the polygon and viewer sees only the edge, and it simplifies the visibility testing, makes rendering faster. So two way, one is through the equation, another one is through the angle. Okay, and So although we are having some limitation here in the backface detection, so the limitations are uh, it requires storage of detailed polygon and the object information. That is one way, one thing, and it works only with the correctly for completely closed solid object. Okay. For example, if one face cube is removed, the inside becomes visible, right? So and the algorithm cannot determine the visibility properly. There is a drawback in that. And the third limitation is it works perfectly for the convex object. However, for concave objects, so one visible polygon may still be hidden or behind the another visible polygon. There is a problem in the concave object. So therefore, the backface detection is this is a simple method, but it alone not sufficient for the complete hidden surface removal. Okay, so that is what the backface detection. So let us move on to next method, next algorithm, which is depth buffer method or Z buffer method. So it is one of the most widely used visible surface reduction technique in computer graphics. Okay, so unlike backface reduction, it is image space method. So the backface is actually object space. So image space means again you think about the pixel. So pixel by pixel. So instead of comparing the entire polygon, we are comparing only the pixel level. So for every pixel on the screen, the algorithm stores the depth value of the nearest surface. Okay, and whenever the another surface is projects onto the same pixel, the depth values are compared. So the surface closest to the viewer is displayed, and the method is very fast, simple, efficient, and highly suitable for the hardware implementation. So this is the reason why we are considering the Z buffer algorithm or Z buffer technique. So we are having some steps in this algorithm. Let us examine the algorithm one by one. At the step number one, we have to do initialization. So depth buffer stores depth value. Frame buffer stores the pixel color. So initially, the depth buffer is set to 0. That is, depth buffer of x comma y is set to 0, and frame buffer is equal to the pixel color or background color. BG color is a background color. And step number two, for each polygon on one at a time, for every projected pixel, calculate the depth value z. So depth of buffer x value x comma y, you calculate the z value, that is a depth actually. Okay, so compare the depth value with the stored depth buffer value. So compare the current depth with the uh, and with this depth buffer value. So based on that comparison, you can update the depth buffer and the frame buffer. Okay, so otherwise ignore the pixel. So this process continues until all the polygons have been processed, and finally the frame buffer contains the visible image. So for every pixel, calculate the uh, depth value and compare it and update the um, depth buffer and the frame buffer every time. Okay, once everything you have to repeat it. So once everything is done, so you will be getting the visible image in the rendering. So calculating depth is repeatedly for every pixel is expensive, right? So to improve the efficiency, the polygon surface can be used like this: z equal to minus ax minus by minus d divided by c. So the ABCD are the parameters of the plane. Already we discussed. XY is the plane. So once the depth value is one pixel is known, so neighboring depth value can be computed incrementally. Okay. For horizontal movement, z dash equal to z minus a by c. Similarly, for incremental calculations can reduce the cost significantly. For vertical movement, z equal to z plus b by c. So that is the another one. And as a result, the Z buffer algorithm remains one of the fastest visibility technique. Very simple. So calculate the depth, update the depth, and depth computation is given like this. So if it is horizontal movement, Z dash is used. Vertical movement, Z is actually used. Okay. And even though Z buffer is popular, efficient, we are having some drawbacks here. So Z buffer method is it stores only the depth value per pixel. So therefore it can display only the nearest surface. So this will work perfectly for the opaque objects. Okay. However, the transparent surface is again a challenge in the Z buffer method. For example, the glass windows, water surfaces, transparent plastic objects, images. So these are all opaque. Opacity is high, so that it is a challenge in the Z buffer method. So in these cases, multiple surfaces may contribute to the final pixel color. The standard Z buffer method cannot handle these kind of situations, glass windows, water surfaces efficiently. So to overcome this problem, A buffer method may be uh, suited well. So that is the next algorithm, A buffer method. So A buffer method is called as accumulation buffer. So it is an extension of Z buffer method. So it was originally developed by developed at Lucas Film Studios as a part of RES rendering systems. The goals were transparency in handling the pixels, anti-aliasing support, and improved image quality. So unlike Z buffer, so which stores the information about only one surface, A buffer can store the information about multiple overlapping applications. That is what shown in the picture. Okay. This makes it suitable for realistic rendering like water, plastic, transparent. So those objects can be rendered easily. And so A buffer is uses more sophisticated storage mechanism. So each pixel can store, for example, if you take a single surface, if only one surface exists at the pixel, the buffer behaves like a normal Z buffer method, a Z buffer method. It stores only depth and the RGB color or BG color. And coming to the case two, um, if you're having multiple surfaces, so the case one is it is having a depth and RGB, the case one. So it doesn't have any multiple surface, only one surface means. If you're having multiple surfaces, in that case, um, if several surfaces overlap, the buffer stores the pointer to a linked list. So each like a linked list. So the information will be stored in the linked list: surface one, surface two, surface three, and so on and so forth. Each node in the linked list represents one surface. Okay, and contributing to the pixel. So thus, like this, multiple surfaces can be processed simultaneously. So if you're having only one surface, it acts like a Z surface, Z algorithm, Z buffer algorithm. Otherwise, it uses a linked list to store the information. Each node contains the one surface information, oh, to the pixel. Okay. So each node in the A buffer linked list shows the detailed information like RGB components used to determine the surface color, opacity value for adjusting the transparency, depth value for distance, finding the distance from the viewer, area coverage, surface identifier, additional rendering parameters um, used for advanced shading and lighting calculation. So, at the final stage, the depth and opacity information are combined to calculate the final pixel value or final pixel color. So, this produces the smooth edges and realistic transparent effects in the computer graphics. So, in this session, we discussed the three algorithms: backpaste reduction, depth buffer method, and the A buffer method. So, thank you for watching this session. So, see you in the next session. Thank you.